This is note 7.4, and we're going to call this characteristics of solids. And specifically, we're going to be looking at the different types of interparticle forces, IMFs, and covalent bonds and ionic bonds, and what those look like on a macro scale. Up until now, we've been talking about microscale things, right? IMFs and all these little teeny tiny interactions. So now let's look and see how they look on a larger scale. And the first thing we need to do is rank the particle forces. So ranking the particle forces. On one side we have, let's go and draw this. On one side we have intramolecular. And on the other side we have intermolecular. That's going to be IMFs. Okay. On the intramolecular side, we have ionic and covalent bonds. And these things take place within the molecule. Take place within the molecule. In other words, they're chemical bonds. Okay. And what does that mean? The atoms are physically bonded to one another. Atoms are physically they're physically bonded to each other. Okay, that's one type of interparticle force. The other is IMFs, okay, intermolecular force, and that takes place outside. Takes place outside and between molecules. Examples of those are hydrogen bonding, dipole-dipole, and London dispersion. And we said that hydrogen bonding is stronger than dipole-dipole, which is stronger than London dispersion. And we gave examples of what hydrogen bonding was, and dipole-dipole interaction was, and all that type of thing. And then we even looked at, we did an activity. We did an activity where we looked at the paperclip on water. We floated it, and we also put drops of water on a penny to form a bubble, and that bubble was held together with this kind of a skin, for lack of better terms. And anyway, the reason all that was able to happen with water is because of these hydrogen bonds. Okay, so that was a characteristic of hydrogen bonding. Water sticks together. It's got a sticky quality to itself. Obviously, the water's not sticky, but it sticks to itself. Okay, so let's go ahead and rank all of these in order of strength now. In order of strength. Before, we just ranked these in order of strongest to weakest. Now let's look at all of them together. First, the bonds. Ionic is going to be, generally speaking, stronger than covalent, which is stronger than hydrogen bonding, which is stronger than dipole-dipole, which is stronger than London dispersion. Oops. I should have done this. Stronger than London dispersion. Okay. if we were to rank those in order of which is the strongest to which is the weakest. So you can see here very clearly that, I'm going to do this in red because otherwise it's not going to, this right here, okay, look. You can think of it like this. Here's the IMFs, and here's chemical bonds. The chemical bonds are much, much stronger than IMFs. So when you're thinking about this stuff, you group chemical bonds first as stronger than the IMFs. Okay, by far, by a long shot. So what does that mean specifically? And what does it look like? Okay, so we're talking about these little teeny tiny interactions, but what happens is once these things start to repeat over and over and over again trillions of times, you start to get these larger solids. And I'm going to get to this in a second. But we can look at this solid, and I can tell you right now what type of an interparticle force is composing this thing. Okay, and you will be able to as well by the time we get to the end of these notes. So again, what do they look like on a macro scale? On a macro scale, you're going to start seeing things like this, or you're going to start seeing water that forms drops, or things that melt at various different temperatures. Okay, that's what this affects. So without further ado, let's just start talking about some of it. What do they look like? Here's your question. What do these forces look like in solids? Well, answer. Different types of solids exhibit different characteristics. We run out of room. Different characteristics. Okay, so let's look at the first one, ionic solids. Okay, it's formed by repeating ionic bonds. Okay, so for example, here would be a chlorine atom. Okay, and here's a sodium atom, right? And actually this is chloride. Well, let's say that we bring it together and it loses, sodium loses this electron over here to chlorine and it becomes chloride. This picks up a charge. So what happens is these two now bond together tightly, okay, in an ionic bond. It's a very, very strong bond. And this pattern of sodium and chlorine will repeat over and over and over again trillions and trillions of times. Okay, and it forms a lattice structure. Okay, this is called a lattice structure. Okay, this is a lattice structure. When you repeat this thousands and trillions of times, you get a lattice. I'm going to pause and then I'm going to draw it, and you can draw it as well. Okay, when you take this principle and you start to repeat it over and over and over again, you form this lattice structure. And notice you'll have a negative chlorine, positive sodium, negative chlorine, positive sodium. So these are ions, they're ionically bonded. Okay, this is going to be a nonmetal. A negative nonmetal, that's how we know. And if this is a positive metal, and they repeat over and over and over again. And whenever you do that trillions and trillions of times, you get a nice crystal lattice. Okay. Examples are salts, basically. Examples are salts. So again, a salt is just simply any metal and nonmetal bonded together. And over time, if you do this trillions and trillions of times, over time you get these crystalline structures. Okay, that's Copper sulfate, it's a metal and a non-metal. This has a lattice structure to it. If we could zoom in, we would see this copper bonded to a sulfate over and over and over again, and it forms these crystal lattices. And these things have very, very high melting points. So let's talk about some of their characteristics, okay? Some of the characteristics include high melting points, we'll say, it says here in the notes 200 to 2500 degrees C, but honestly I think this lower end is much, I think it's much higher than 200 to 2500 degrees C. In general, salts are more like over here, I think. They conduct electricity. When dissolved in H2O. Or when molten. Molten just means to add a lot of heat and melt them. Okay, like in a volcano. Like that's what we're talking about. A volcano is molten. Lava is molten rock. And they're hard and brittle. Oops. Brittle. Hard and brittle. I'm going to stop here because this is going way long. So I'm going to stop and we'll do another 1 or 2 parts.